And thanks for the introduction. Today I'm going to be talking a little bit about some work my colleagues and I have been doing on semantic adversarial analysis with formal scenarios. So given that this is the workshop on adversarial analysis, adversarial examples in the real world, I'll start with adversarial examples. We'll get to the real world a little bit later. So the context for this work really is that there's a number of us in formal methods have gotten interested recently in trying to analyze systems that use machine learning components. And such systems are very difficult for kind of our traditional techniques and formal methods for a variety of reasons. And adversarial examples are an area that's particularly interesting to us because it's sort of a small, well-defined area within the broader question of verification of AI-based systems that maybe we can get some traction on. But at the same time, there's some issues with adversarial examples, and so I'll get to that. So one way that I like to frame this is a phrasing due to my old advisor, Sanjit Sesha, is if we think about the sort of traditional classical adversarial examples for neural networks, things like we'll take an image and we'll apply some mutation, usually at the pixel level, and you can, with high probability, trick a particular classifier. And this could be a very serious issue if you have something like a safety critical system, say a self-driving car, which is using a neural network to identify stop signs, say. And the fact that these networks are sensitive to tiny amounts of pixel level noise is very disturbing if we're going to be giving control of safety critical systems like cars to such systems. But of course, there are some questions about this type of example. So for instance, an obvious one which has been discussed is, can these mutations occur in practice? Is this a reasonable attack model for your system? And arguably, even if they can't occur in practice, these clearly show that these systems are not learning the concept that we intend for them to learn. But in any case, it's not super clear whether being able to find pixel level adversarial examples implies anything really about the real world performance of these kind of systems. Whereas one of the things that you would see in practice, for example, is maybe not pixel level perturbations to a street sign, but viewing it from a different angle or a different position, say. And so because of that, people have started looking into different types of mutations to images. So big mutations, for example, that would be huge perturbations if in L2 norm or something like that, the traditional kinds of perturbations, but are more realistic, like translations, scaling, and so forth, which are more realistic attacks in some sense. However, even if you move to that kind of, that type of adversarial example, which has been nicely called semantic adversarial examples by Sesha and others, where you're looking at semantic features, so to speak, of the space, instead of looking at perturbations in the actual input that is going to the network. You have a higher level abstract space, which I'll talk about a little bit later, which parameterizes the inputs in a semantic kind of way, like the positions of street signs, for example. And perturbations in that space may correspond to huge perturbations in a very nonlinear kind of way in the underlying input space. And so it's not clear how you could apply necessarily the same techniques, although there's been some progress on that front using, say, differentiable renderers, for example. But even if you move to that kind of semantic adversarial example, there still remains the question of what is the impact of that kind of an input on the entire system? If you have something like a self-driving car, the car is not just a neural network. The neural network is probably being used for perception or maybe also prediction or some other things. But it's just a single component in a larger system. And just because you're able to fool the perception component, say, into giving an incorrect answer for a single frame or even over some period of time, doesn't necessarily imply that you will have problematic behavior at the system level. And so for that reason, what we've been looking at for the last few years is trying to analyze AI-based systems in a way that looks at semantic features, positions of objects, time of day, other types of semantic information that are meaningful in the application domain, but also at a system level, trying to find counterexamples, failures that occur in the combined system, not just in an individual component. So the outline for the talk today, I'm going to start by describing a couple of tools that we've developed over the last couple of years, VerifAI and SCENIC, which work in this paradigm of trying to find adversarial semantic adversarial examples, basically counterexamples that are found in this high-level space rather than the pixel space of images in a high-level space of parameters. And these tools are designed to be applicable to any type of system. They're not specific to any particular domain. And so I'll tell you a little bit about the architecture of these tools and the overall methodology, illustrated by some examples and mentioning some of the use cases we've used them for. And then to make everything more concrete, I'll talk about two very recent application studies we did applying these tools. One was a kind of complete design flow for a neural network-based aircraft taxiing system, an industrial system from Boeing, where we showed how you can use these tools to model the system and its environment, perform falsification, so deliberately a search for violations of system-level properties, like not crashing. Debugging failures. So once you have an adversarial example, trying to understand why it happens, there's more hope of doing that with semantic adversarial examples than pixel-level ones. And finally, retraining. So now you have a bug, you understand sort of at least why it happened. Can you do anything to prevent it happening again? So I'll also talk about retraining and actually eliminating some of these bugs. Then the next case study I'll look at has the virtue of, maybe it's not as in-depth as the first one, but it gets to the real-world aspect of all of this. So in that case study, what we did is we found adversarial examples in simulation and then tested them in the real world on an actual self-driving car and found failures in the real world. And then I'll wrap up with some high-level conclusions. Okay. So to start out with, VerifAI is an analysis toolkit for AI-based systems that we introduced last year, which provides a unified framework for various design tasks, such as modeling, falsification, debugging, or even synthesis, trying to solve for parameters of your system that will lead to good performance. And VerifAI uses a very generic, high-level structure. It's designed to be modular, so you can plug in different simulators, different search techniques, etc. So let me give you a high-level idea of how that works. There are three types of inputs to VerifAI. One is a description of the system that you're interested in, which actually can be a black box. Basically, all we need is that you are able to simulate it. We're working now actually on incorporating white box reasoning techniques into VerifAI. If there's interest, I can mention some work along those lines at the end. But for now, you can think of it as just being a black box sort of system. Second, an environment description. And for something like a self-driving car, say, this can be very difficult in itself. Just describing what the possible environments for a system like a self-driving car is a very difficult task in itself. And so one of the main points I'll be talking about today, this idea of formal scenario, is something that we've developed to help with exactly this problem. How do you formally specify a very complicated kind of environment that involves physical objects potentially moving around dynamically? And so the SCENIC language is a tool we've developed to help with that, which I'll come back to in a few minutes. Okay, so once you've got a description of the system and its environment, now that you have those two things, you can hope to do some kind of analysis as to whether or not your system works. But the last component you need is a formal definition of what it means for the system to work. So that is what we call a formal specification in formal methods. This is a property usually expressed in logic, which describes something that needs to be true about the system. So in the context of adversarial examples, it could be something like a local robustness property. that all the points in the input space within a certain radius in L2 norm, say, around a particular image, are classified the same way. That would be an example of a specification. Here, we're more interested in system-level specifications. So not on the neural network per se, but on the entire system. So it could be for a self-driving car that the car, for example, never comes within half a meter of another object. That would be an example of a system-level specification, which you could formulate in a temporal logic, for example. OK, so once you have these three components, the first thing that VerifAI does is construct what we call an abstract feature space. And this is really the heart of this idea of a semantic adversarial example. Instead of searching through the raw input space to the neural network, we have this abstract feature space, which is parameterized by things like positions of objects, say. And there's a transformation from that space to the actual input space of the system. So in the case of self-driving cars, where you're maybe using a neural network for perception, the transformation would be a renderer or even a simulator if you're running dynamic simulations, something which can take this high-level description and convert it into actual input data. So once we have this abstract feature space, then we search through that space using a variety of techniques, ranging from simple random sampling to cross-entropy optimization, simulated annealing, some general global optimization techniques. And every point that we generate in this space is then fed to a simulator, which is not built into VerifAI, but VerifAI can interface to a variety of different simulators. I'll show a number of examples later. And the results of running those simulations are gathered up by VerifAI, and VerifAI monitors whether the specification you've provided is satisfied or violated. And that information is used in a couple of different ways. First of all, it can be used to inform search. So if you find, for example, that you're getting close to a violation, where closeness can be quantified by some concepts in temporal logic falsification, for example, then we can use that to direct the search towards, in the direction that seems to be leading to failures, for example. So for instance, like a global optimization technique would do exactly this. Secondly, though, we save all of the information about the runs we generate in an error table, and we can do a post hoc analysis of that table to try to analyze why bugs occurred, for example. Do maybe a sensitivity analysis. Which features was the system most sensitive to? And we'll see examples of this later. So this general framework can be used for a variety of different use cases. Let me just illustrate it with one particular example. Say we want to falsify a collision avoidance system. So we have an ego car on the left here on this road. It's driving along and eventually encounters this disabled car, which has some traffic cones in front of it. And the ego car has a camera on the front, which produces images like this. And a neural network is taking those images and trying to estimate the distance between these two cars to decide when it should switch from lane keeping to maybe when this distance drops below some threshold to doing an emergency lane change, getting into the other lane, and then switching back to lane keeping. So this is a very simple toy example of a system. And what we mean by falsification is we're trying to answer a question like, does the system always avoid a collision? So we don't care necessarily of, does the network always estimate the distance to within some accuracy? What we want to know is, does the system avoid a collision? And so falsification is the term in formal methods for an automated search for inputs, here basically the environment conditions here, which would cause the system, not just the neural network, to violate its specification. And so we can do that in VerifAI. I won't go through the details here. Basically, once we've defined the environment, which we can do using the SCENIC language that I'll describe later, we can describe this semantic feature space of parameters to search through. So that's what we're doing towards the top of this little input to VerifAI here, defining the space of parameters we can search through, which here consists of, like the initial position of some of the objects, controller parameters, like the speed that the car should be maintaining, this sort of thing. We're specifying what type of sampler to use. In this case, we're going to use cross-entropy optimization. So that's one of the active sampling techniques in VerifAI. We're giving the system-level specification. Here, this is a metric temporal logic formula, which is asserting that it's true at all time steps. It's globally true that you don't collide with any of the 3 traffic cones. And then we can set up and create the falsifier in VerifAI. And when we do that, what happens is like this. So what's being shown here is a render in the Weebots simulator of the simulations that we were running. And now VerifAI is starting the first simulation. So you can see the ego car is starting out doing lane keeping. Then it does the lane change, successfully detects the car, it changes lanes. So now I'm showing at higher speed here, VerifAI running many simulations. Eventually we get the first collision. So here the car just grazes the traffic cone. And now our cross-entropy sampler is zeroing in on that part of the space. So now it's reliably producing crashes, various variations on that crash scenario. And the last one that we'll see is an interesting case here where we actually get a different kind of failure where the neural network thinks this orange car is a large traffic cone, so makes the lane change too early. The controller assumes we were going at a higher speed than we were at that point, so we fail to complete the lane change and we get a collision anyway. So this is just an example of VerifAI at work. But notice that one of the things I didn't explain here is how did we get this initial kind of configuration with this car and the traffic cones? We don't want to have to hard code that sort of scenario. Even though this was a quite simple one, you could imagine a much more complex one. So there's this more general question of if you have a complicated sort of cyber-physical system like a self-driving car, how do you generate meaningful environments for it? It's all well and good to generate adversarial images, but are those actually meaningful? Even if we move to a space of semantic parameters, it's not clear whether we will get out meaningful environments. So to make that a little bit more concrete, the point I'm getting at is that the semantic feature space, even once you've moved from the space of pixels, which is huge, to a space of semantic parameters, it's still large. So for a single car, you might have parameters like the model of the car, its position, orientation, the background, where you are in some global city, say, that you're simulating, the color, and global parameters like weather and time of day. So it's a large, high-dimensional space still, and it's unstructured. If you positioned 12 cars at random on a road, you're not going to get a realistic scene. They're going to be intersecting each other, or even if you rule that out, some will be facing the wrong way. They won't be in lanes, and so forth. Realistic scenes have complex geometric constraints that restrict what types of data, if you will, that you want to generate for these kind of systems. And furthermore, you might be interested in particular types of data. Like you might want to know, how well does my system perform on the highway or in a dark alleyway with a double parked moving van, right? There we have some constraints, very specific constraints on the data we want to generate. We can't just use a GAN to generate kind of arbitrary traffic scenes, say. So the solution that we've proposed to this problem is to use what we call a formal scenario. So a scenario defined in a language that has a formally defined semantics. So SCENIC is a scenario description language that we've developed for this purpose. SCENIC is a probabilistic programming language that defines distributions over scenes. So for example, here are images rendered from a SCENIC program for bumper-to-bumper traffic. So that's a very general specification of a scenario. And you can see here where these are 4 independently sampled realizations of a scene from SCENIC. And you can see we get quite different scenes, but that all reasonably meet this criterion of being bumper-to-bumper traffic. And this is only about 20 lines in SCENIC, even though this is a quite complex sort of scene, because SCENIC provides readable, concise syntax for common geometric relationships. And furthermore, because it's a domain-specific language, we're able to do things like have domain-specific sampling techniques. So we can generate scenes in a more efficient way than a general probabilistic programming language would be able to do. But at the same time, we get some of the power of probabilistic programming languages. So over just like a purely generative model, we have the ability to impose declarative hard and soft constraints. So for example, it's built into SCENIC that objects cannot intersect each other. You will never get a scene where that happens. Okay, so let me give you an example of what SCENIC looks like by going through this example of a badly parked car. So we want images like this one, say. How can we describe this in a formal scenario? So the first thing we're going to do here, I'm showing kind of a schematic on the left-hand side of the scenario we want. In the top left is the ego car, and you can see its view cone in blue here. And on the bottom right is a badly parked car. So it's kind of by the curb, but it's a little bit far away, and it's pointed at an angle. The first thing we're going to do is import everything specific to this case study, which we did in the GTA 5 game, from a library we've written. SCENIC is not specific to GTA or to even self-driving cars. So we wrote a library that defines the concepts of, like, what is a car? What is the curb? That's a region, a primitive data type in SCENIC that defines some positions in space. And the road direction is a vector field. That's another primitive SCENIC type that describes where things are, that describes the nominal traffic direction at any given point on the road. So we can create an ego car. We're not saying where it is, which means SCENIC is going to use the prior distributions on all of its properties, position, color, and so forth, defined in the class car. Now, to create the badly parked car, we're going to start by taking the curb region. We're going to pass it to this built-in function visible to find the visible part of the region. Zooming in here, that would be this black highlighted part of the curb. Now we're going to pick a random point on that curb. The way we're going to do that is we're instantiating this class, oriented point, which is a built-in class in SCENIC, on that region. So on is what we call a specifier. It's one of a variety of ways that SCENIC provides for describing in a concise and readable way where something is positioned. And in this case, it means essentially uniformly at random within that region. So once we have that random spot, we can then pick an angle for the car to be parked at, and we're saying it's uniformly random, 1 or -1, so left or right, times a uniform distribution over the interval 10 to 20 degrees. Once we have that angle, now we can say create a car to the left of that spot, offset by ½ meter. This is just the syntax for creating ½ meter to the left in SCENIC. And notice, in order to create the car ½ meter to the left, we need to know how wide the car is. Because if the car was wider, we'd have to put it further away from the curb, or further to the left, so that its right edge was ½ meter from the curb. So this is a nice feature of SCENIC's specifiers here, is that the left of specifier will automatically work out that before we can evaluate this expression, we need to sample the width of the car. Then we can determine the position. And finally, we'll say facing this funny angle, not in the global coordinate system, but relative to the direction of the road at that point. And again, SCENIC can work out that it first needs to figure out where the car is before being able to look up the road direction and then compute this orientation. So this is a complete SCENIC program. And if we sample scenes from this and put them in GTA 5, we get images like this. So indeed, there's a car by the side of the road, but at a bit of a funny angle. But we left a lot unspecified, like the distance to the car, the time of day, and so forth. So we get quite a variety of these possible images that meet this high-level description. OK, so SCENIC can be used for a variety of different applications and different domains. Like here, I'm showing a robotic planning application. For example, exploring system performance by generating specialized test data, debugging a known failure by generalizing in different directions, and designing more effective training sets by training on hard cases. So I'll illustrate this using a couple of case studies. All right, so first I'll talk about this case study on a neural network-based aircraft taxiing system. So we applied this to a real system from Boeing, in collaboration with Boeing, a neural network-based taxiing system we showed a complete design flow for this system. So modeling runway scenarios in SCENIC, falsifying the system, debugging it to find distinct failures and their root causes, and finally retraining the system to eliminate failures and improve performance. So let me just say a bit about TaxiNet. This is an aircraft taxiing system developed by Boeing. How it works, and it's an experimental system, I should say. It uses a neural network that takes an image like this one, and then estimates from that image the cross-track error. So that's the distance to left or right of the center line of the runway. That goes into a controller, which then controls the steering and throttle of the plane. And the system level specification here was that the plane should track the center line to within 1.5 meters. And we can write that down in metric temporal logic as follows. Details aren't important, but basically this is saying that within 10 seconds, we get within 1.5 meters of the center line and then stay there for the entire simulation. So we modeled this using SCENIC with a variety of semantic features like time, clouds, position of the plane, and so forth. Here's the SCENIC program. So for example, we're starting out here by putting some distribution, a uniform distribution on the time of day between 6 a.m. and 6 p.m. These lines here are putting actually a non-uniform distribution on the rain and cloud types. And here we're putting the plane up to 8 meters left or right of the center line, up to 2,000 meters down the runway, 30 degrees uniformly at random, left up to 30 degrees left or right uniformly at random. So using this, the distribution defined by this SCENIC program, VerifAI can then generate tests and run simulations and monitor that property. And if we do that, we did falsification, we run 4,000 simulations. What we found is that the system does not do all that well. In fact, in 45% of cases, it violated the spec. In 9%, it actually left the runway entirely. So then we can analyze what went wrong. And we did, by looking at the error table collected by VerifAI, we found several types of failures. For example, this is performance of the system plotted over time of day, where above the dotted line is you satisfied the spec and below you violated it. You can see there's quite a bit of variation. And in fact, there's several reasons for that, but one that we found by looking at the data here was that we noticed that in the middle of the day versus in the afternoon, the shadow of the plane comes into the image. So we hypothesized that maybe that's confusing the neural network. So SCENIC makes it easy to test that hypothesis by just changing the program to say, okay, disable rendering of shadows. And so, in fact, follow-up experiments here did confirm that the root cause of this particular bug were due to the plane's shadow. So then we could do retraining. We use this distribution from SCENIC. We can write a SCENIC program that has a wide variety of times of day and so forth, shadow positions, etc., to generate a new training set. So we trained a new version of the system with the same size training set, but different distribution, and we got much better performance. So in this example, the original system on the top here overshoots the center line and goes off the runway, whereas the retrained system on the bottom accurately tracks the center line. And this wasn't just a fluke. In fact, in general, we found much better performance. So the percentage of cases where we violated the spec and left the runway decreased significantly. And we can see also that in this particular bug of the time of day dependence was eliminated. So here in blue is the retrained system, and you can see that the performance is uniform across the entire course of the day. One thing I don't have time to get into, but is in the paper, is we can actually not only manually specify these distributions, but actually use cross-entropy optimization to learn good training distributions. All right, so let me check the time. Oh, we may have started a few minutes late. How much longer should I go for, Adam?
So I would say maybe 2 to 3 minutes.
Okay, then I'll just very quickly go through this second case study and then conclude. All right, because I want to get to the real world aspect. So this showed we can find semantic adversarial examples in simulation, but what about reality? So the idea here is that we can use formally guided simulations guided by these formal scenarios to design real world tests. So we demonstrated this in an industrial case study with AAA and LG. You can see the details in the paper that will be coming out in a couple of weeks at ITSC. Where we basically tested both in simulation and at a real-world facility. So the idea is to analyze failures in simulation to select cases for track testing. So we create a simulated world, we specify the scenario using SCENIC, and specify safety properties and metrics using metric temporal logic or some other formalism that VerifAI can support. We use VerifAI to do temporal logic falsification. That generates safe and unsafe test cases in simulation. We can then analyze those test cases and select particular test cases to run on the real-world track, execute those on the track. Of course, track testing is expensive, so we'll generate thousands of simulated cases, but only test a handful on the real track. And then the test data that we get from the track allows us to analyze, does the system really have these vulnerabilities in the real world? So in this example, what we did is we took a real self-driving car running the Apollo 3.5 self-driving stack, and we looked at this scenario where you have a car that is turning right, and there's a pedestrian crossing the road on this over here that hesitates partway through its trajectory. So we wrote a SCENIC program describing that scenario. I won't get into the details, but this is using actually a dynamic extension of SCENIC that we developed recently that allows you to talk about events happening over time. If you're interested, let me know. We actually just gave a webinar on this. I'd be happy to direct you to the link on that. We ran falsification, so we generate thousands of simulations, around 1,000 simulations here, around 2% of which violated the safety property, which here was no collisions. And based on some analysis of this data, which I won't get into here, we picked several examples to run in the real world. So ones where we robustly got a collision versus not robustly did not get a collision, and intermediate cases. And what we found is that these actually transferred to reality quite well. Of the cases that were unsafe in simulation, most of those were unsafe on the road, and the ones that were safe in simulation, most of them were safe on the road. So I'll just show you this one example. Here's a case where you can see the pedestrian coming on the right. Here's the self-driving car. The self-driving car detects the pedestrian and brakes, but then loses track of the pedestrian and inches forward, ultimately running into it. Okay, so I won't get into how we diagnosed what went wrong there, but we can replay the data, basically. The conclusion is that adversarial semantic examples like this can help you find failures in the real world. Okay, so just to conclude, oops, sorry, my animation didn't work here. The takeaways here are that in order to ensure the safety of machine learning-based cyber-physical systems, we need to consider system-level semantic adversarial examples. And formal scenarios provide a precise, interpretable way to model the environments of such systems and guide testing and retraining. And VerifAI and SCENIC are open-source design and analysis tools based on this paradigm that are applicable to realistic industrial systems. And we've showed we could use them to find and diagnose bugs, then eliminate them through better training set design, and find adversarial examples not only in simulation, but actually transfer those to find bugs in the real system. For more information, I encourage you to go to our website here where we have documentation and many more examples and links to the papers.